But what I wanted to do today was talk to you guys about stoichiometry and how to solve stoichiometry problems. And then if you guys have any questions concerning either the midterm or the lab, um, you can go ahead and fire away towards the end after this particular discussion. Stoichiometry is always intimidating because there's a lot of math, and I know that many students who take chemistry really have a difficult time with the math. But if you can add, subtract, multiply, and divide, then you're in good shape because that's the math that you need in order to do stoichiometry. So the other thing that you need to understand is how to use your calculator. What I found out in the past was that um, you you have the problem all set up, but you're putting in the numbers incorrectly in your calculator because you're using the wrong function. So I need to guide you in terms of how to use your calculator. And each calculator is going to be different, whether you have a TI or a Sharp or a Casio, but the essential steps are pretty much very similar. So when we get to that part where you're doing the calculation in a problem, I'll pause a moment and then show you how to punch that into your calculator. I'll spend the first part talking about how to solve stoichiometry problem, and then make sure everyone's okay. And then if you have questions, whether it be in the lab activity or any questions, chapters 1 through 7, I'll be more than happy to guide you or explain any discrepancy you might have. What I want to explain to you in this particular section, chapter 7 is about quantitative, figuring out the amount of chemicals that either you need or will produce. It's kind of like if you cook. If you cook, you know you need starting ingredients. If you don't have all the ingredients, you can't make the proper product. Okay. Yeah, you can substitute here and there, and your product is going to change slightly depending on what you substitute, but you need the proper ingredients. In chemistry, when we deal with a reaction, we call that the reactant. Those are the chemicals that you use as your resource in order to produce the product. And then what you will do is you put all the ingredients together, and then depending on the timing, depending on the conditions, you will get a product. Sometimes you might be able to create a whole dinner, or maybe it's just one dish. In chemistry, what happens is that you might be able to produce one product, or maybe you're going to get a product and other chemicals that goes with that. But it's basically the same thing. The amount that you start with, okay, the total amount in mass has got to be the same as the total amount in mass of your product. That's because of the conservation of mass. You can't create or destroy matter. You can only convert it from one form or the other. Okay. Now in cooking, you might say that's not true because I start with so many pounds or ounces of an ingredient, and I might have less or might be more, but you've actually lost some due to maybe losing it during the process, or maybe you add water or something like that, or the water or the liquid evaporates while you're cooking it. But in chemistry, you always have to deal with the law of conservation of mass. The atoms that you start with is equal to the atoms that you end up with, just arranged differently. Okay, so keep that in mind. So let me go ahead and get started here, and then let you know what's going on here. So we're talking about chemical reactions, and what I want to share with you is what we talked about last time. The type of stoichiometry problems that you have is you have a chemical, and that chemical has different atoms involved, and you might have the mass of that chemical, and you want to know exactly how many molecules are in that chemical. So if you got like 100 water, okay, 100 water molecules. And you know that water is 2 hydrogen and 1 oxygen. Then how many atoms do you have? Well, if you've got 100 water molecules, then each water molecule is 3, then you can do the conversion factor. For every 1 molecule, there are 3 atoms. So 3 times 100, you get 300 atoms at the end, okay? 200 of them will be hydrogen, 100 of them will be oxygen. In chemistry, it's very hard to count individual pieces. Why? Because they're so small. So what we do is we bundle it. Suppose we have our 100 water molecules, and we say, okay, for every 25, we'll call that a bundle, okay, for lack of a better term. Then for our 100 water molecule, then we have 4 bundles, because each of the bundle will contain 25 water molecules, okay? Well, that's the same thing as the mole. Okay, the mole is just a way of grouping the individual atoms or molecules, it depends on what you're talking about, so that it's easy to count. And so what we say is that we have 6.02 times 10 to the 23rd. Yeah, that's a huge number, 6.02 times 10 to the 23rd, but atoms are so small. And we call that bundle, not a bundle, but a mole, okay? So depending on how many molecules we have, we can bundle it into moles, okay? So if we have like 3 moles of water, well, if we have 3 moles of water, then we have 3 times 6.02 times 10 to the 23rd. Why? Because for each mole, 1 mole equals 6.02 times 10 to the 23rd. So 3 moles would be 18.06 times 10 to the 23rd. It's just 3 times 6.02 times 10 to the 23rd. So I hope you have a good understanding of why we use mole, because again, atoms are so small, we need to group it so that we can make the counting process easier. So if you look at this slide right here, what you will see is that we can classify matter in terms of the mass. We can weigh water. We say we have 18 grams, we have 36 grams, okay? And in that 36 grams, there's going to be so many molecules, or there's so many bundles, so many moles, okay? So we can start with the mass of water or the moles of water, how many moles of water, or the molecules of water. So that's what this particular slide shows you. In order to convert the mass of water to moles of water, you need to figure out how much does each water weigh. Okay, you got to figure out how much each water weigh. Now, if water, and you guys know how to calculate this, water has 2 hydrogens and 1 oxygen. Each hydrogen has a mass based on the periodic table of 1.0 atomic mass unit. So 2 hydrogens will weigh 2.0 atomic mass unit. It so happens that oxygen has a mass of 16.0 atomic mass unit. So together, 1 water molecule weighs 18.0 atomic mass unit. It just so happens, and this is the amazing part about the mole, that if you have 18 grams of water, that translates to 1 mole, okay? It just so happens, and someone came up with that, guy by the name of Avogadros, Amadeo Avogadro. He took a molecule like water, and he put it on the, well, he didn't really do this, but you can think about it. He put 1 water molecule on a scale, another water molecule on a scale, another, and kept on adding it until the scale read 18 grams. And when he counted those water molecules, he found out there was 6.02 times 10 to the 23rd. Okay, carbon it weighs 12 AMU. So if you take 1 carbon atom, put it on a scale, 2 carbon atoms, 3, and keep adding it so that the scale reads 12.0 grams. Guess how many carbon atoms you have? You have 6.02 times 10 to the 23rd. That's why 6.02 times 10 to the 23rd is so important. And that's why we use the molar mass, because when you have the molar mass of that chemical, that represents 1 mole. So if you have 36 grams of water, guess what? 36 is twice 18. You have 2 moles. And you can do that via the conversion factor. If you take 36 and you use the conversion factor that every 18 grams equals 1 mole, then 36 divided by 2, 2 moles. Okay, and that's what you see right here. In order to go from, let's see, in order to go from mass of a chemical to the moles of the chemical, you need the molar mass of the chemical that you have. If that chemical is a molecule, you use the molar mass of the molecule. If that chemical is an atom, then you use the atomic mass of that atom. If that chemical is an ionic chemical like sodium chloride, then you use something what we call the formula weight. Okay, it's just the sum of the atoms for one molecule, converted to grams per mole. And then this conversion factor right here is what I told you what one bundle represents. One bundle represents 6.02 times 10 to the 23rd, and we call that 1 mole, Avogadro's number. So you cannot go from mass to molecules directly. You first, at least in chemistry, need to figure out how many moles you have, and then use this Avogadro's number. Now that you know how many moles, then you can say, okay, that many moles multiplied by 6.02 times 10 to the 23rd will give me the number of molecules or the number of atoms. Okay, so that's why I like to teach stoichiometry based on dimensional analysis, because the best way to work stoichiometry is not overthink the problem. That's why you guys will get confused of chemistry, because there's so many ways to ask the question and you start overthink it. If you just distill it down to the basic, what do I have? What am I calculating? Then you can use this map, the stoichiometry map, to carve yourself a path, carve yourself a calculation path to get to the answer. Okay, so this would be like if you have a compound. Okay, a compound, and a compound would be like H2O or CH4 or KMNO4. Okay, those are compounds. Compounds are unique chemicals that have bonded atoms and they have a unique identity. But suppose I want to know, okay, I've got KMNO4 right here, and I want to know what mass of oxygen is in 1 mole of potassium permanganate, KMNO4. Well, if I have 1 mole of potassium permanganate, I don't really have a way to figure out what mass of oxygen there is. I need a different path. And that's where this comes in, okay? This second leg is for the elements in a compound, like KMNO4. I want to know about the oxygen in KMNO4. Guess what? The formula of a compound is the conversion factor. It relates KMNO4 to oxygen. What you can say is that for every 1 KMNO4, you have 4 oxygen. Because in KMNO4, you have 1 potassium, 1 permanganate, and 4 oxygen. So you can use the formula as a conversion factor. Now, what we do in chemistry is that we don't want to deal with 1 molecule, although you could. What we say is that, okay, we have 1 mole of KMNO4. Guess how many moles of oxygen we have? Well, if the ratio is 1 molecule per 4 oxygen atoms, then the ratio is also going to be the same. 1 mole of KMNO4 equals 4 moles of oxygen. Okay, so that's why the mole is so deceptive, because it represents either individual pieces like a chemical, a molecule, or the atoms in that piece. So we can make the conversion factor here. 1 mole of KMNO4 equals 4 moles of oxygen atom. Now, when we're talking about the elements in a compound, we're talking about the elements. In a chemical reaction, when I say methane reacts with oxygen, I don't mean this. Okay? Because in a chemical reaction, you use the chemicals that is most readily available. Oxygen is not readily available in our surroundings. What is readily available is oxygen, the diatomic chemical. So when we're talking about oxygen, the atom within a compound, we're talking about the element, the individual element. But in a chemical reaction, when we say methane reacts with oxygen, you better write O2, because that's how the chemical is available for this reaction to occur. Yes, I know it's very deceptive. That's why you need practice. You need to understand the way these terminologies are used. And you guys don't have that experience, but that's why I'm trying to point that out. So let's go back in this. Remember, I asked you, okay, I have 1 mole of KMnO4. What is the mass of oxygen? Well, the question is, well, the information is I have 1 mole of KMnO4, mass of oxygen in KMnO4. Okay, so I have a starting point. That's the information, and I have a destination. I have a starting point and I have the destination. You can always distill a stoichiometry problem in that matter, your starting point and your destination. This is a molecule, so I'm going to start here. This is an atom, so I'm going to end up here. I'm going to end up here. I have a mole, so I'm starting right here. Okay, I'm looking for the mass, so I'm ending up here. So the path that I'm going to follow, the calculations that I'm going to follow is I'm going to start at D, but then I can't go to W directly. There is no bridge to get there. I have to get there by these stepping stones. These stepping stones are the conversion factors. In order to get to W, I need to first go to Y, and then from Y, I can do W. And then between D and Y, I need the chemical formula. This stuff right here, that's what I need. For every 1 mole of KMnO4, I have 4 moles of oxygen. And I'll have the moles of oxygen right there. And then from Y to W, I need the mass of an element, the atomic mass. AT means atomic. The atomic mass. And I know for oxygen, it's 16. Oxygen, the molecule, is 32, but oxygen, the atom, is 16. So this is the way I would solve this problem. Again, showing you, instilling in you to use dimensional analysis. Okay, this is what I want to show you. We're going to start with 1 mole of KMnO4. And I've got 2 conversion factors, 1 here and 1 here. So I'm going to do 2 conversion factors. That's on my first, that's my second, and then I'm going to get my answer. Okay, depending on how many stepping stones you have, that's the number of conversion factors. My first one is for every 1 mole of KMnO4, I have 4 moles of oxygen. Now this will take me from D to Y. If I stop my calculation there, I would get the moles of oxygen in KMnO4. Okay, but that's not the question. The question is, what mass is that? So I need to do the second step, and that second step requires me to use this, the atomic weight of oxygen. You see this right here? That's going to be how I'm going to set up the next conversion factor. I got to have moles on the bottom. That way it cancels. I know that for every 1 mole of oxygen, remember oxygen, 1 mole equals 16 grams. That's the atomic mass. And I have 16 grams up here of oxygen. The units have got to cancel. The units have got to cancel. And if I take 1 times 4 times 16, I've got my answer, 64 grams. 16 times 4 times 1 is 64 grams. See how easy that is? You take the thought process of overanalyzing it and you distill it down to what do I have, where am I going, and how do I set up the problem? And that's how you should approach every stoichiometry problem. Okay, every stoichiometry problem. And again, that's why I give you this map so that you can do that in these seems like complicated type of questions. And it's really not. but you have to get used to reading the question. So let me move on, okay? I wanted to at least break that in to you guys so that you understand why I teach stoichiometry via dimensional analysis. So this is for one compound. This is for one compound, KMnO4, H2O, CH4, NaCl, and the atoms within that compound. But if you have a chemical reaction, okay, if you have a chemical reaction, then you've got one compound and you need to relate it to a different compound. And the way they're related is through the balance equation. It's through the balance equation. You use the coefficient in the balance equation to relate how one chemical is related to another. And that's the only place you use the balance equation. The coefficients in the balance equation, it's a conversion factor. Just like the formula is in a for a compound, KMnO4, 1 potassium, 1 permanganate, 4 oxygens. In a balance equation, the coefficient in each of the chemical, those are your mole ratio. Okay, and I'll try and explain that. So this right here, you see how this is a mirror image of this? And it's related through the balance equation? That's because once you get to the other side, the other compound, the other chemical, then you will be calculating the moles, because these are the landing points, moles. And then you can calculate the mass or the molecules based on that moles. Or if you want, if you have the moles of that compound, you can figure out the mass within the atom of that compound. Okay, so that's what this is all about right here. Okay, later on, you guys are going to see a shortened version. It still gives you the same idea. Okay, this right here, this basically is the same thing as this. See how you have B? Well, B is just that. D is just that. You have the balance equation. You've got 4, that's just that. And you've got 2, that's just that. Okay, and then you know how you go from 4 to 3? Well, 4 to 3 is just that. Here are your conversion factors, the items in the box. Those are your conversion factors. So this is just a different view of this. And the reason why I show you the top one is because later on, you guys are going to expand this to include stoichiometry using gases, stoichiometry dealing with solutions. Right now, we're just looking at the basics. Okay, so you want to be able to use both. So let's move on. Here's a typical example. I've got nitrogen and hydrogen producing ammonia. It's a very simple example. You need to first, let me tell you a secret. Don't ever assume an equation I give you is balanced. Always double check, okay? You guys now have the skill to balance a chemical reaction. So I'm going to challenge you to double check any equations that I give you and make sure it's balanced, okay? If you just take it at face value and think that it's balanced, most likely it isn't, okay? So when you start, even if I give you coefficient in front of those chemicals, double check, make sure it's balanced. Here I've got 2 nitrogens in N2. Here I've got 6 hydrogens in 3H2. In 2 ammonia, I've got 2 nitrogens and 6 hydrogens. So the equation is balanced. This is a balanced equation. If there's nothing in front of the nitrogen, it means it's 1. It means it's 1. So 1 nitrogen molecule will combine with 3 hydrogen molecule to produce 2 nitrogen molecule. Yeah, that's great if we're dealing with molecules, but I don't want to deal with molecules. I want to deal with the gram quantity, the macroscopic scale. The macroscopic scale deals with grams. So in order to go from molecules to grams, I need the mole. The mole is a magnifier. So these numbers right here also represent something called the mole ratio. the mole ratio. If I have 1 mole of nitrogen, it combines with 3 moles of hydrogen to produce 2 moles of ammonia. I got 1 bundle of nitrogen to react with 3 bundles of hydrogen to produce 2 bundles of ammonia. Okay, again, that's why we use mole frequently in chemistry, because we don't want to deal with individual pieces. We want to deal with a greater quantity, things that we can measure in lab, grams. And remember, nitrogen, it's 28 AMU, it's 28 grams equals 1 mole. Hydrogen, it's H2, that is, it's 2 AMU, it's 2 grams per 1 mole. Ammonia, it's 17 AMU, it's 17 grams per 1 mole. That's why we like the mole, because then we can start measuring the grams, okay? And grams we can measure in the laboratory. You guys weigh grams all the time in your scale in the lab. So here's a typical question. I have 84 grams of nitrogen. I have 84 grams of nitrogen. And the question is, look at the data that you have, okay? Look at the data that you have, because the data that you have will also signify the number of significant figures that you should have in your answer, okay? 84.0 is 3 sig figs, 3 sig figs. Your final answer better have 3 sig figs. If you ever want to know how many significant figures should I round off my final answer, go back to the question. Look at all the numbers. Find the one with the fewest significant figures. That's the number of significant figures that your answer should be rounded off to, because that's the data that you're given, okay? It's not rocket science. All you do is look at the question, scan all the numbers you're given, and find the one with the fewest significant figures, because your answer is going to be based on that. When you multiply and divide, your answer is always rounded off to the number with the fewest significant figures. And guess what? In stoichiometry, we're always multiplying and dividing. Okay, so again, I always tend to do this, is I break off in a trend, but stuff that you guys should know. Stuff that you guys should know. I've got 84 grams of nitrogen with excess hydrogen. Whenever you see excess hydrogen, it means that it doesn't run out. It means that you don't have to be concerned with that chemical. You never use that chemical, the excess, to figure out how much product you produce, because you've got the nitrogen is going to be the chemical that runs out first that will determine how much product is produced, okay? The nitrogen would be the limiting reagent, the hydrogen would be the excess, and you're trying to figure out how much ammonia is produced. And when you say how much, it's usually how many grams. How many grams, okay? So if I have 84 grams of nitrogen and I see from the balance equation it's a 1:2 ratio, don't do this. 168 grams of ammonia will be produced because of that 1:2 ratio. No, because the 84 grams represents different amounts of nitrogen molecules. The different amounts of nitrogen molecules will produce twice as many ammonia molecules, but the 84 grams is not going to give you 168 grams, okay? That's because the nitrogen needs to bring in hydrogen for the ammonia to produce. So don't ever do mass to mass. You always have to go from mass to moles. Now you know the individual pieces. Moles of one chemical to moles of the second chemical through the balance equation, and then I convert that moles to mass. So that's what we have right here. That's what we have right here, okay? Never do that. Never do that. You need to figure out how many nitrogen molecules, how many nitrogen moles you have, and then you can figure out how many ammonia moles you have, and then you convert moles of ammonia to grams of ammonia using the molar mass. That's the key. So when you have a balance equation, it not only shows you the individual atomic ratio, the molecular ratio, but it shows you the bundle ratio. 3 hydrogen molecules reacts with one nitrogen molecule to produce 2 ammonia molecules. But if I have 30 hydrogen molecules, then I would need 10 nitrogen molecules to produce 20 ammonia molecules. These numbers just give you the ratio. So whether I have molecules, this is my abbreviation for molecules, by the way, MOLC, okay, parentheses. Or I have 10, it's 10 to 30 to 20. Or I have 100, it's 100 to 300 to 200. Or I have a trillion, 1 trillion to 3 trillion to 2 trillion. Or more importantly, I have moles, 1 mole to 3 moles to 2 moles. It's much easier in chemistry to deal with moles, okay? That's because 1 mole represents that many grams of that particular chemical. Again, the magic of the mole. That's why we use it. That's why we use it. So when we do a stoichiometry problem, like I said, it's kind of like cooking or assembling a bicycle, or assembling a toy or something that has parts. Let's do the bicycle analogy. I have another analogy. It's the car analogy, and you probably see it in my lecture notes, but I'm going to go to the bicycle analogy because I want to keep the slides a little bit short, and it serves the same thing. I have a bicycle. The bicycle, when you put it together, we will need 2 wheels, 1 body, 1 handlebar, and 1 gear chain. Together, that equals 1 bike. Again, the parts make up the whole. The parts make up the whole, okay? And now you have the relationship of wheels, body, handlebar, and gear chain to make that one product. But suppose I tell you I have 40 kilograms of wheels, 25 kilograms of bodies, 3 kilograms of handlebar, and 2 kilograms of gear weight. How many bikes can I produce? You'd be scratching your head and say, well, I don't really know, because I don't know how many wheels are in 40 kilograms. And I don't know how many bodies are in 25 kilograms. You don't know how many pieces you have, because you need to know the pieces in order to figure out how many bikes you can potentially produce. Just like in chemistry, you need to know how many molecules, how many moles, before you can figure out how many products you can produce. You can't go with grams. So if I know how much each wheel weighs, then I can figure out how many wheels are in 40 kilograms. If I know how much each body weighs, then I know how many bodies are in 25 kilograms. That's the same reason why you need the molar mass of a chemical, because if you know the mass of each chemical and you've got the mass, then you know how many moles that represents. That's the key, because when the reaction occurs, you need to know the mole to mole ratio, the parts to part ratio. That's the key to solving these problems. You can't go from mass to mass. You got to go from mass to parts, parts to parts, parts to the whole product. Okay, so let's say that after I do my calculation, I have 8 wheels, 5 bodies, 6 handles, and 5 gear chains. Well, 8 wheels will potentially give me 4 bikes. That's the theoretical amount. Okay, theoretical. Theoretical just tells you potentially how much you can produce. Okay, if you had unlimited parts of the others, if you had unlimited parts of the others, 8 wheels, 8 divided by 2, here is the conversion factor, 8 wheels, and we're using our, remember this is 1 bike, and we know that 2 wheels equals 1 bike, so I can potentially make 4 bikes. Again, I'm showing you dimensional analysis. 5 bodies, well, 5 bodies, and I know from my equation that 1 body equals 1 bike. So potentially I can make 5 bikes from those bodies. See how I'm doing dimensional analysis? Same thing in chemistry. This will potentially give me 5 bikes 6 handlebars will potentially give me 6 bikes, and 5 gear chains will potentially give me 5 bikes. The amount that is the smallest, this is a big hint. The amount that is the smallest is what you're going to end up with. Why? Because the wheels will run out first before the other parts. So using this list, I'm going to end up making 4 bikes only. And then the others will be extra parts, like what you see right here. Okay, what you see right here. 4 bikes, you got an extra body, you got 2 extra handlebar, and you got 1 extra gear chain. This is the problems that you guys are going to be solving. Okay, when you get lost in the chemistry, because it can be intimidating, you're throwing in chemicals in there. You not only got to read the chemical formula, you got to figure out the molar mass and all that. Go back to the simple analogy. Think about bicycles, okay? Because it's not that hard. But it is hard because they throw in all these other vocabularies. That's why it takes practice. So let's go back to our problem, nitrogen. Okay, we got 84 grams of nitrogen. I want to know how many moles that is. Okay, so here it is. I've got mass of nitrogen, 84 grams. I need to calculate the moles of nitrogen using the molar mass of nitrogen. Remember, nitrogen in this particular case, according to the balance equation, is N2. That's 28.0 grams equals 1 mole, And I write it this way so that if you write it this way, 128 grams per mole, then you start biasing yourself. You start thinking that the grams always has to go on top. And it doesn't always have to go on top. It can go in the bottom so that the units cancel. That's why I like to write it this way. That way you have the independence of either putting the grams on the bottom in your conversion factor or on top. Okay, that's the first thing that we need. We need to convert that 84 grams of nitrogen to moles of nitrogen. Then we use the balance equation, this right here. And according to the balance equation, for every 1 mole of nitrogen, I produce 2 moles of ammonia. And this is the only time you use the balance equation, when you're relating one chemical to the other. You don't use it any other time. You might say, a lot of students will say, okay, this is 28. And then you see that, I'll do it in the next part. This is the typical mistake that I always see. Okay, I'll do it in this next part. Now that you have moles of ammonia, right here, when you make this conversion factor from here to here, then you need to convert it to mass of ammonia, and you need the molar mass of ammonia right here. And the molar mass of ammonia is 17.0 grams equals 1 mole. This is the mistake that many of you will do. You will see 2 right here, and you're thinking that you got to change that to 34. 17 times 2. No. It's the molar mass of the chemical. The chemical is NH3. It's not 2NH3, it's NH3. The molar mass of NH3 is 17 grams equals 1 mole. The only time you use the balance equation, the only time you use the coefficient is right here. That is the only time. You don't make 1734 just because you see a 2 in front of that. Ammonia is NH3. 1 ammonia, 17 grams equals 1 mole. Okay, so please don't make that mistake. That's what I see a lot. Okay, the chemical is NH3, 17 grams per mole, not 34. Just because you see a 2 there, don't multiply it by 2. That 2 shows you the relationship between this ammonia, this hydrogen, and this nitrogen. That's the only reason why you put that there. Now that we have this, then we can solve this problem. You've got all the steps, you've got all the information you need. It's just a matter of stringing it together via dimensional analysis. So again, if you want to look at this map, and here, this map shows you that later on, we're going to do solution chemistry. Later on, we're going to do gas laws. But right now, we're just concentrating at this part right here. this part right here. We've got the mass of ammonia. We're going to calculate the moles of, sorry, the mass of nitrogen. We're going to calculate the moles of nitrogen, the moles of nitrogen to the moles of ammonia, the moles of ammonia to mass of ammonia. The conversion factors are molar mass of nitrogen, balance equation, molar mass of ammonia. Same thing as that previous stoichiometry map. Here, you just got to get used to it because this is a more general view in terms of showing you how you can use dimensional analysis for solution chemistry as well as gas laws, as well as gas law. Yes, someone asks, is all chapters in the midterm? Yes, chapters 1 through 7. A heavier emphasis on 7, but chemistry is a cumulative thing. You can't forget one. You can't, without understanding how to use that knowledge in the later chapter. Okay, if you don't know how to write chemical formulas, then you're not going to do well in stoichiometry. Okay, so it is cumulative in that respect. So here it is. This is the strategy. Okay, the first is to convert mass of nitrogen to moles of nitrogen. That's B to D according to our map. The second is to convert moles of nitrogen to moles of ammonia. That's D to 4 according to our map. And then the last is to convert moles of ammonia to mass of ammonia using the molar mass of ammonia. That's D to 2. So in this particular case, this is the first step, and I'm showing it to you in a step-by-step basis, and then I'll show it to you as we string it in one equation. 84 grams. Notice I have grams here. Your conversion factor has got to have grams in the denominator. And you're using the molar mass, 28 grams on the bottom, 1 mole on top. That way the grams cancel. And what you end up with is moles of nitrogen. Moles of nitrogen. Then our second step is we have, this answers 3 moles of nitrogen. Our balance equation shows us that for every 1 mole of nitrogen, there's 2 moles of ammonia. That's from the balance equation, the 1:2 ratio. Okay, that is the mole ratio. So when we do this map, we get 6 moles of ammonia in H3. That's D to 4. And then finally, we convert the moles of ammonia to mass of ammonia. We take our number 6, and you see how you have moles here? Well, that has to have moles in the denominator for the units to cancel. The molar mass of ammonia, 17 grams equals 1 mole. The moles have got to be in the bottom. The number 17 has to be on top. That way you know you're multiplying 6 times 17 and not taking 6 divided by 17. The units will tell you how to set it up. So in this respect, what we have is 84.0 grams of nitrogen. And remember, I said there are 3 conversion factors because I read my stoichiometry map. And then I get my answer. Grams of nitrogen, moles of nitrogen. What I'm going to show you is that I'm not even going to put in the numbers. I'm just going to let the units walk me through, because that's the key. Then this is my molar mass. And then the second is my balance equation. And you see this right here? Moles of nitrogen has got to be in the bottom. Moles of ammonia, therefore, is going to be on top. And then the last conversion factor is molar mass of NH3. See this right here? Moles of ammonia has got to be in the bottom. They always have to cancel. They always have to cancel. Because if they don't cancel, you're messed up. And then grams of ammonia here. Then I'm just going to put in the numbers. I know that there are 28 grams per 1 mole. I know that for every 1 mole of nitrogen, I produce 2 moles of ammonia. And I know that 17 grams of ammonia is 1 mole. That's the 3 steps that I just showed you. What you would do in your calculators, you would take 84 divided by 28, multiply by 2, and multiply by 17. You see how you have ones here? any number multiplied by 1 or divided by 1 doesn't do anything. It gives you the same number. So skip that step. Skip that step. Take 84, divide by 28, multiply by 2, multiply by 17, and you get your answer. You should try that. You should try that. Because what you end up doing a lot, especially if you're very cautious, you say 84 times 1 times 2 times 17 divided by 28 divided by 1 divided by 1. You're just wasting time. You're just wasting time. Just take 84 divided by 28 times 2 times 17 equals. You get the answer. And that answer happens to be, guess what? That answer happens to be 102. So if you have 102, congratulations. You did a stoichiometry problem using dimensional analysis. That's the key, dimensional analysis. Okay. So let's go to a harder problem. Okay, let's go to a harder problem, because that was all nice, but you know that chemistry can be very intimidating. Here again is the stoichiometry map. We went from B to D to 4 to 2. Suppose it was a liquid, okay, and I want to know what is the volume of that liquid. You need the density. Density is a conversion factor that relates the mass of that liquid to the volume of that liquid. Suppose I have the moles of a chemical and I want to know the individual molecules. Use Avogadro's number. So again, this stoichiometry map is more general, but it serves the same thing. You go from 4 to whatever this number is. Okay, I think this is number 3, and you're using these guys as your stepping stone, your conversion factors. Okay, so I don't know why I have this. Oh, this is just a summary of what we did. B to D, D to 4, 4 to 2. That's basically what we did in our previous problem. Okay. In fact, almost all stoichiometry problems are going to be of the kind that you just saw. Grams to grams. Given X grams of A, how much of C or D is produced? Mass to moles, moles to moles, moles to mass. You just have to figure out which chemical you're shooting after. Given X grams of B, how many C or D is produced? Again, mass to moles, moles to moles, moles to mass. Given X grams of C, how much D is also produced? Mass to moles, moles to moles. Now you're using the balance equation that relates C to D, moles to mass. It's always those same sequence, always those same steps, but there's so many ways to ask a stoichiometry problem that you get overwhelmed by it. But the skeleton, the setup are all the same. That's why stoichiometry should not intimidate you, especially if you know how to approach it using dimensional analysis. Figure out what you have, what the question provides, figure out what you're calculating, and figure out the path to get there, and then set it up using dimensional analysis. That's the key. Okay, so all of these different types of questions, same structural calculation. Here's a it looks like an intimidating problem. Okay, if 35 grams of potassium permanganate is mixed with 45 grams of hydrochloric acid, what mass of chlorine is theoretically produced? Now, when I say theoretically produced, again, depending on which chemical is the limiting agent, that's how much chlorine I'm going to produce. Okay, so the chemical, either potassium permanganate or the hydrochloric acid, whichever gives me the lowest amount of chlorine, that's the answer. That's the answer that's going to solve this problem. Okay, if only 10.3 grams of chlorine was collected in synthesis, what is the percent yield? This is something that you also need to know, and we'll tackle this when we solve this first part. So when you have a problem like this, the first thing that you need to do is you need to balance the equation. You can't do a stoichiometry problem with an unbalanced equation, because if you're relating one chemical to the other, you got to see what that relationship is. okay? It may be by coincidence, it's a 1-to-1 ratio, or maybe it's a 2-to-2 ratio, which distills down to 1-to-1. But you're lucky if that's the case. So the first thing that you want to do is balance the equation. I got 1 potassium here, 1 potassium here. We got 1 permanganate here, 1 permanganate here. Remember what I showed you last time, that you want to save the chemical with only one type of element as your last step. So I'm going to save chlorine as my last step. So 1 potassium, 1 potassium, 1 permanganate, 1 permanganate, 2 hydrogens here. Okay, I mean 2 hydrogens here. So I need to put a 2 right there. Okay. Oops, I forgot something. Let me erase this real quick. Okay, I want to balance the oxygen next. 1 potassium, 1 potassium, 1 permanganate, 1 permanganate, 4 oxygens. I have, oops, 1 oxygen in water, so I need to put a 4 right here. I need to put a 4 right there. That way I have 4 oxygens in both sides. Now I look at my hydrogens. I've got 8 hydrogens here, and I only got 1 here, so I need to put 8 right there. So this is 1, this is 1, this is 1 so far. Now look what happens because I save chlorine as the last step. Now I can balance the chlorine without affecting any other atom. That's the trick I want to show you. Let me get to that when I have time. Someone was asking about the stoichiometry activity. That's in lab, right? So the next thing we want to do is balance the chlorine. Here we have 8 chlorines, so we need to put a 4 there. That right there would be the balance equation. Double check. And so that's the answer in this particular case. And what did I mess up? Oh, I forgot. Okay, I got another chlorine right here. I forgot about that. So I can't put 8 here, even though this is 8, because 8 plus 1 equals 9. 8 plus 1 equals 9. So I can't do that. I overlooked this. So I need 8 chlorines here. Okay, I've already got 1 right here. So how do I make this 7? How do I make that 7? Because 7 plus 1 is 8. Well, 7/2 is the key. Use fraction. 7/2 times 2 is 7, plus 1 is 8. Now all I need to do is I need to multiply this whole equation by the oh, maybe you guys caught me. I'm being lame. Okay, let me do this again. I can't put 7/2 there because I have a chlorine here. I have a chlorine here. Yeah, don't do this. I have a chlorine here, I have a chlorine here, and I have chlorine there. I forgot about that chlorine. So I've got 3 chlorines right here, and I've got 2 there. So I need 8, so I need 5/2 here. 5 plus 1 plus 2 is 8. So the fraction I need is not 7/2, but 5/2. Okay, 5/2 times 2 is 5. 5 plus 1 is 6, plus 2 is 8. That would be the balance equation. Then I just multiply this whole equation by 2. So this right here will convert to 2. This right here will convert to 16. This right here will convert to 5. This right here will convert to 2, 2, and 8. That would be the balance equation. Okay. Don't do like me where you get lost. It must be my dyslexia in forgetting about the other elements in the compound. So that's basically what we have right there. That's the balance equation. Let me clear this. 2 to 16 to 5 to 2 to 2 to 8. That's the balance equation. So the problem here is to start with 35 grams of that. We're at B, and we want to know chlorine. So B to D, D to 4, 4 to 2. Just like the previous problem. I need to know the molar mass of potassium permanganate because that's what I need right here. And I need to know the molar mass of chlorine because that's what I would use right here. Then the balance equation is that for every 2 moles of KMnO4, I have 5 moles of chlorine. That's this right here. And I would use that in here. Okay, that's one problem. You still have a second problem, and that second problem is hydrochloric acid, this guy right here. And for this problem, I would do the same thing. I would first get the mass of hydrochloric acid, 45, convert that to moles, convert that moles to moles of chlorine, and then I can figure out the mass of chlorine using that. So I have 2 problems in one. Here's the molar mass, by the way. I give it to you. For potassium permanganate, I have 158.0 grams per mole. And for chlorine, it's hydrochloric acid, it's 36.5 grams per mole. So let's go ahead and work on this. Let's go ahead and work on this, okay? Let me do this real quick. I need to take a screenshot. That way I don't lose sight of this, okay? Because I'm going to go to a blank page next. So let's do the KMnO4 first. KMnO4 analysis, KMnO4 analysis. Remember what I told you, there's going to be 3 conversion factors, just like the last time. And the first one is going to go from B to D, and then D to 4, and then 4 to 2. So according to the problem, I have 35 grams of KMnO4. And then I have 3 conversion factors. And then I have my answer, okay? The first conversion factor is the molar mass of KMnO4. So in the previous page, I told you it was 158 grams equals 1 mole. So grams here, 1 mole of KMnO4 right here. And then the balance equation is the next conversion factor. And according to the balance equation, for every mole of KMnO4, I have moles of chlorine. Again, I'm not putting in the numbers because I want to show you that it's all about the setup. The numbers will come later. And then finally, I have the molar mass of chlorine. And the molar mass of chlorine is 70.9 grams per mole. 70.9 grams per mole. So I'm going to put, see how I have moles right here? I'm going to put moles of chlorine right here. And I'm going to put grams right there. Then I just need to put in the numbers. For potassium permanganate, I have 158 grams, 158.01 mole. The balance equation tells me that for every 2 moles of potassium permanganate, I have 5 moles of chlorine. Okay, the numbers goes with the unit. And then finally, the last step is molar mass of chlorine. And that molar mass is 70.9 grams. See how I have grams right here? 70.9 has to go with that, 1 mole. So you just do the math here and you have your answer. And then the second setup will be this for hydrochloric acid. You would say, okay, the problem gives me 45 grams of hydrochloric acid. So that's what I'm going to start out with, 45 grams of HCl. And again, I have 3 conversion factors. The first one is the molar mass of hydrochloric acid, grams of HCl, moles of HCl. And then the second one's the balance equation, moles of HCl. I'm always letting the previous unit walk me through the next conversion factor. And I've got moles of chlorine. Letting the previous unit walk me to the next step. And then the molar mass of chlorine. Then I have my answer. So what is the molar mass of HCl? It's 36.5. 36.5 grams is 1 mole. What is the balance equation? It's 16 moles for every 5 moles of chlorine. 16 to 5. And then what is the molar mass of chlorine? I have it up here, 70.9. Okay, so when you do this, and let me share with you my calculator. so you guys can see what's going on. So the first one, I'm just going to do 35 grams. And I'm going to divide by 158. And I'm going to multiply by 5 and divide by 2 and multiply by 70.9. Then hit equals. 39.26. According to my problem, I have 3 significant figures. So I'm going to say it's 39.3. 39.3 grams of chlorine. That's for the first one. Okay, let me do the second one. So this is a clear 45 grams divided by 36.5 times 5 divided by 16 times 70.9 equals, and that's 27.32 or 27.3 using 3 significant figures. This is my answer. This is my answer. Why? Because it's the smallest amount. This is my answer. Set up. Again, you can see that the first conversion factor is the molar mass of KMnO4 or HCl. The second is the balance equation that relates HCl to chlorine or KMnO4 to chlorine. And then the last is going to be the same because you're ending up with chlorine. Okay. And the smallest amount is your theoretical yield. That's the amount that you will get because the other chemical is going to run out. I mean, this chemical is going to run out. The other chemicals in excess. This chemical, that your limiting reagent will always be based on the chemical that runs out first. Just like the bike, the 8 wheels will run out when you produce your product. The others are excess. Okay.
Excuse me, Professor.
Yes.
The question is to percentage. We should multiply.
The question is. The second part is percentage, okay? That's the second part. We haven't solved that yet.
Okay, thank you.
Okay, we haven't solved that part yet. I'm just solving this part right here. So theoretically, we can produce 27.3 grams of chlorine. That's the amount. Now, the next question is, okay, so you know, based on your ingredient, like if you're baking cookies, okay, they tell you you need to have half a dozen eggs, you gotta have so many pounds of flours and this and that, a stick of butter here, and you can get 3 dozen cookies based on the ingredients. So what happens when you start baking cookies and you start eating the dough and then your kids come and start messing around? And instead of 3 dozen, which is what the recipe said you have, you only make 2 dozen. So 2 dozen is the actual. 3 dozen was the theoretical. The theoretical. So what was the percent? Well, you know that the percent yield, let me change my pen. Okay, let me change my pen. The percent yield, how efficient you were in baking those cookies, according to the direction, was you only made 2 dozen, but theoretically you could have made 3 dozen. Okay, so like I said, you've got the Duncan Hines recipe based on the ingredients, based on the box, you can make 3 dozen. So you go ahead to the kitchen, you start doing this and that, and you start cheating by eating the cookie dough, and your kid starts doing that as well. And you lose some because, well, something happens. So this is the actual, you only came up with 2 dozen, but you could theoretically have made 3 dozen. So guess what your efficiency is? 2 divided by 3 times 100, you got a 66%. So if you only were able to isolate 10.3 grams of chlorine, that's the actual. But this is the theoretical, 27.3, based on everything converting over, no waste. Then the percent yield will be the actual over the theoretical times 100. So that's just the actual 10.3. This was collected in the synthesis, 10.3. This number has always got to be less than 100. If it's more than 100, guess what? You could win the Nobel Prize. You just invented matter. It's not the case. 10.3 divided by 27.3 times 100. That's your percent yield. And you see that in the next page here. Okay, you see that in the next page here. Oops. See that in the next page here. Okay, these are just the calculations. If you read the lecture notes, 39.3, which was correct in what we got, and then 27.3, which was correct in what we calculated. And this is the last part, the theoretical yield, actual over theoretical. So the just like the bikes, if we were able to produce 123 bikes a day, but we only produce 63, then the efficiency, the percent yield would be 51. For our case, it was 10.3 over 27.3. I believe that was the number that we had. Okay, 27.3 times 100. That is our percent yield, and that number comes out to 10.3 divided by 27.3, 100. We only have a 37.7% yield. It's not a difficult calculation. You would have to be given the actual value right here. So make sure you understand if you're given a problem, which is the actual, what you get when you do the experiment, what you get when you actually do the process, versus the theoretical, which is what you get when you do the calculation. Okay, times 100 because it's a percent, and then that's the number that you have. So that basically is what we have right there. Okay. And that's the extent of the stoichiometry that you will see for this class. We don't need to do anything else past that. And the rest of these are just examples of doing the same thing. It's doing the same thing, okay? And showing you how to use a stoichiometry map to solve these problems, okay? How to use a stoichiometry map to solve these problems. So you should practice it so that you can see and get proficient in doing these things. Because as much as I talk and try and bring it down to the basics, until you do it, until you see that, yeah, this makes sense, you're not going to get it in your mindset. You have to practice doing it. You have to practice doing it. This right here, that's your activity. And let me give you a preview. It's mixed between balancing chemical reactions, dealing with the moles, and then stoichiometry at the very last. Okay, right here is atoms, molecules, moles, Avogadro's number. How many atoms are in 11 molecules of sulfur hexafluoride? You know, sulfur hexafluoride is SF6. If one has 7, how many does 11 have? Okay, so that's the question. And then this right here, balancing equation and the mole concept. This is where the stoichiometry comes in. Write the balance equation and the chemical equation when potassium chloride, KCl, is combined with oxygen, O2, to produce potassium chlorate, KClO4. Okay, KClO3, I mean. I tell you what it is. So you need to write the balance equation first, and then you can do this. I tell you 17 moles of potassium chloride is combined with excess. What amount of potassium chlorate is produced? So that one's not so difficult. Let me show you where you would use what the sequence is for that particular problem using the stoichiometry map. Go to my website, go to Fog Links, go to either information and equation. And information and equation, there's a equation page right here for your midterm. Here you have the molecular geometry. Here you have the solubility rules, but here's the stoichiometry map. Here's the stoichiometry map and the periodic table. So this question that you saw in the activity, I tell you that you have 17 moles of KCl. Well, you're starting right here, moles of KCl, and you're trying to calculate the mass of KClO3. So you're going from D to 4, 4 to 2, D to 4, 4 to 2. So the first thing you want to do is convert the moles of KCl to moles of KClO3 using the balance equation, and then use the molar mass of KClO3 to convert moles of KClO3 to mass of KClO3. We're not going from mass to moles, moles to moles, moles to mass. We're going from moles to moles, moles to mass, because the question is right here, okay? You got 17 moles of KCl, excess oxygen. Determine the mole. Oh, you're not even calculating the mass. You're just calculating the moles of KClO3. So you're just going from D to 4. You're using one conversion factor. Okay, that part is pretty straightforward. This next question right here, write the balance equation, combustion reaction of sucrose. So whenever you hear that word combustion, you know that sucrose, C12H22O11 plus oxygen goes to carbon dioxide and water. Then you have to balance it. Okay, determine the moles of water produced when 5 moles of sucrose and 39 moles of oxygen round to 3 significant figures. So in this particular case, it's like our second problem. You have to figure out how many moles of water is produced from 5 moles of sucrose, and how many moles of water is produced from 39 moles of oxygen. The lowest one is going to be your answer. So again, going back to this, all we're doing is going from here to here and figuring out which one's the smallest using the balance equation. So that your activity is still there. It hasn't been lost. You just have to find it in Canvas. Okay. So if you can do these activities, okay, if you can do those problems in my notes, you're good to go. Stoichiometry, dimensional analysis. That's the way you want to approach it. That's the way you want to approach it. So I want to spend the rest of the time talking, answering any of your questions that you guys might have in the previous chapter. Okay, in the previous chapters that you might need clarification on. Download this sheet right here, the equation page, because it's very useful. That way you're not searching everywhere in your book. And that page is found right here under FOG links. Okay, right here under FOG links on my web page. You go there and then you click on information and equation. If you want a list of polyatomic ions, because you guys need to know polyatomic ions, go right here and get a list of polyatomic ions. Okay, it's right here. You're free to use it, okay, because it's in my website, so you can do that. If you need the tricks that I've used in our review, then go to this page right here, supplement notes and hints, because this will show you how to use the map of the United States to figure out significant figures. This will show you about heating cooling curve that we talked about in chapter 3. This will tell you about how to do the electron configuration using the periodic table. These are just nuclear chemistry. These are the nomenclature for the subatomic particles. This right here will tell you which ions have fixed charge, which ions have variable charge. This will show you about ions that sounds the same, but they are different. This is phosphide. You see how all of this have IDE ending? That's the elemental ion. These are eights. They have oxygen in it. It's an oxy ions. These are ites. They have one less oxygen than the eights. Okay, where phosphate is PO4 minus 3, phosphite is PO3 minus 3. So there is a list there. And then this is the rules for naming. Okay, and then this right here shows you how to create a bond table to do the Lewis structure. And once you have the Lewis structure, this shows you how to get the electronic geometry and the molecular geometry and the bond angles. And this tells you whether the chemical is polar or non-polar. Okay, and this is the stoichiometry map. So I have these resources in this right here, which if you bought the book, this is also embedded in your book because I asked the publisher to do that. But here, it's all in one document. Here, it's all in one document. Okay, this is the stoichiometry map that we've used. This is the full stoichiometry map that we will be using in the future. Okay, so that's the resources that you guys can use. Okay, be familiar with it. Be familiar with it. And that's found in fog links right here. Right here. Okay. So there's a question in the chat that asks, what is the sum of the coefficient when you have carbon dioxide and water goes to glucose and oxygen? Well, when you have this reaction, let me write this down on my iPad so that you guys can see this. This is actually the reverse reaction of photosynthesis. Okay, photosynthesis is glucose plus, no, this is the reverse reaction of the combustion of glucose. The combustion of glucose, C6H12O6 plus oxygen goes to carbon dioxide and water. So this is, this is the reverse reaction of, this is the photosynthesis reaction. So let me do this. And this is generally gas plus water. This is generally gas, goes to glucose, C6H12O6. That's generally a solid plus oxygen. The hint that I gave you is save that chemical for last, in your last step. Why? Because if you start balancing if you save that for your last step, when you change the coefficient for that chemical, you're only affecting one element, oxygen. For all other chemicals, you're affecting two or more. So you want to use this as your last step. Find your most complicated chemical and start with that. Give that a coefficient of 1. Now let's take a look. Okay, let's balance our carbon. Our carbon is 6 carbons here. I need to put 6 right there. I need to put 6 right here. So there's 6 carbons right there. So my carbons are balanced. Then I'm going to balance my hydrogens, 12 hydrogens. My hydrogens right here. So I'm going to put a 6 right here so that I have 12 hydrogens. Okay, my carbons and my hydrogens are balanced. Finally, I can balance my oxygen. I've got 6 here. Here I've got 6. And here I've got 12. So I've got 18 oxygens here, and I need to change this so that I get 18. What plus 6 equals 18? 12. But this is O2, so I need 6 times 2 equals 12 plus 6 equals 18. So that would be the balance equation. Okay, the balance equation would be, change this real quick, 6 to 6 to 1 to 6. And the sum of the coefficient would be 6 plus 6 plus 1 plus 6. That's 19. Okay, So that's basically it. There's another question on the in the chat. Suppose you go out to dinner and you order the prime rib, 24 grams of protein, 0 carb, sounds like a great meal to me, 10 grams of fat, a baked potato, no goodies, 2 grams of proteins, 26 grams of carbohydrates, a serving of broccoli, 5 grams of proteins, 10 grams of carb. So the best way to approach that is make yourself be an accountant. Let me clear this. You guys can take a snapshot of this of your screen if you want. I'll give you a few seconds. Okay. And then I'm going to clear it, because once I clear it, you don't get it back. Okay. So I'm going to clear now. There. So this is what you want to do. You say prime rib. And this is my protein. This is my carb. And this is my fat. So you just make yourself a spreadsheet so that you can account for everything. And according to the problem, I've got 24 grams here, 24 grams for my 0 carbs and 10 grams of fat. Then my baked potatoes is 2 grams of protein and 26 grams, lots of carbs in baked potatoes. So these are grams. Okay. And you've got 0 grams of fat. And then I have my broccoli. And my broccoli has 5 grams of protein and 10 grams of carbs and 5 grams of fat. And let's see, what else do I have? Black coffee. Okay. Joe. 0 grams of protein, 1 gram of carbs, and 0 grams of fat. And then I also have, wow, this is quite a meal. Makes me hungry for dinner. A piece of carrot cake with cream cheese icing, 5 grams of protein. I've got 53 grams of carbs, and I've got 30 grams of fat. And the question is, how many calories? So this is pretty straightforward, okay? If you keep yourself a sheet like this, okay, dessert. Add up all the mass of your protein. Why? Because this is 4 calories, food calories per gram. This is 4 calories per gram, and this is 9 calories per gram. So what you can do is just add them all up, multiply the proteins by 4, multiply the carbohydrates by 4, multiply the fat by 9, and then add up all the calories. So 24, 26, 31, 30, 36 grams. Okay, double check my math. 24, yeah, 26, 36, 31, 32 grams. Double check my math, 36, no, 26, 36, 37, 42, messed up by 10. And then this is 10, 15, that's 45. You can add these two because they're both 4 calories. So 36 and 42 is going to be 878 times 4. 45 times 9, add that together, that's my total calories. So when you do this, again, if you're organized in how you approach a problem, then you won't make silly mistake. If you just try to do this off the top of your head and put numbers everywhere, you're going to make mistakes, okay? Because it's chemistry is intimidating that way. That's why you guys hate it, okay? Because you really got to be organized and you got to know what you're doing. And if you are, this, by the way, is 450 Change my pen here. This is 405. Okay, 45 times 9. 405. And this right here, 78 times 4 is 312. So when I add these two up, it's going to be 717 food calories, which is 717,000 small calories. Okay, it's a lot of calories. It's a lot of calories. So another problem, guys, take a picture of this if you want the answer. Okay, I'll take a snapshot. Okay, and then I will do the next problem. So I'm going to give you 5, 4, 3, 2, 1. I'm going to clear the slate. Okay, tequila has a density. Wow, you guys are really making me hungry. With tequila to polish off my dinner. 78, so tequila. Okay. The density is, and you want to write density this way, 0.78 grams equals 1 milliliter. It's a conversion factor. It's a conversion factor. What mass of tequila will fill 2 fluid ounces? So you got 2 fluid ounces with 1 shot, and the conversion factor is 29.6 mils equals 1 fluid ounce. Okay, so here's what we want to do. We're starting with this. This is our starting point because it says what mass of tequila will fill 2 fluid ounces. So the 2 fluid ounces is what we need, and we need to figure out what mass of tequila will be in there. So that's our starting point. Start with that. So we got fluid ounces, and then the end, we're ending up with grams. This is my starting point. This is my ending point. Okay. So when you do this, 2 fluid ounces. And I'm going to do dimensional analysis, and I probably need a couple of conversion factor. Fluid ounces right here. Where's fluid ounces in my conversion factor? Right here. For fluid ounces, I've got milliliters. Okay. These 2 units go hand in hand. So I want to use these 2 units. I'm not going to put the numbers again because I want to emphasize dimensional analysis. This milliliters right here, that tells you what your next conversion factor will be. Milliliters here, where have I not used milliliters? Right here. So that goes with grams, and then I have my answer. So what are the values? I know that for every 1 fluid ounces, I have 29.6 milliliters, and I know that for every 1 milliliter, I have 0.78 grams. All I've got to do now is the math. I take 2, multiply by 29.6, multiply by 0.78. And that number comes out to, if you guys are going to be nurses, you got to get used to dimensional analysis, because dimensional analysis is also called nursing math. Okay. Or if you're going to go into a medical profession, whether it be a nurse or maybe you want to be a doctor, you want to really ingrain dimensional analysis in your problem-solving technique, because dimensional analysis will always allow you to answer a problem if you don't have the equation. And we're looking for the electron configuration for selenium. The trick is to go to the previous noble gas, because selenium will have 34 electrons. How do you know? It's right here. Atomic number 34, 34 protons, 34 electrons. So in this particular case, let me see if I can't use this as my tool. Okay, so I have 18 right here. So it's going to be selenium equals the argon core. So you want to represent it this way. And that represents 18 of the 36, 34. Okay, so just walk to selenium from argon. You're going to walk here. That's a 4, and this is S, so it's 4s2. And then you're going to go through the D, and that's a 3d10. Remember, the D is always one lower based on the shell. If the shell is 4, this is 3. If the shell is 5, this is 4. If the shell is 6, this is 5. And then we're back to 4. That's 4p, 1, 2, 3, 4. 4p4. 4p4. So in the answer here, you're going to look for argon, so you can throw out A and C automatically. Okay, give yourself the best chance of getting this right. You know, it's not A or C. B looks good as D, but B doesn't have any d orbitals. So that's not good, because 18 plus 6 is not 34. And then you can count 18 plus 4 plus 10 plus 2 is 34. So that is going to be your answer just based on counting electrons. But D is your correct answer. Okay, 4s2, 3d10, 4p4. That would be the correct answer for that. Argon, 4s2, 3d10, 4p4. Okay. If you look at this question on the chat, it says, what is the mass of a thimble of water which contains 4.0 times 10 to the 21st molecule? So we're looking at water, the molecule water. So we're looking at a compound. That's that. We don't have a balance equation. We're not looking at the atoms in water. We're just looking at water, the compound. So we're either sticking to B, D, and C, or 2, 4, and 3. It doesn't really matter. Okay, I'm going to use this side. If you look at the problem, it tells you you have 4 times 10 to the 21st molecules of water. That's this right here, molecules of compound A. Our compound A is water. And that's our starting point. This is our starting point. Where are we going to end up? Look at the question. What is the mass? We're ending up here. What is the mass? So our sequence is C to D to B. Okay. And what are the conversion factors? The first conversion factor is Avogadro's number. That gets us from C to D. Our second conversion factor is the molar mass of water. That gets us from D to B. So I would start with, let's see if I can't do this. Okay. I would start with 4.0. Oops, times 10 to the 21st. That's not very good. I'll just use my finger. Times 10 to the 21st molecules. Molecules, MOLC, of H2O. And then I would use my conversion factor. There's 2 conversion factors in this particular 1, 2. Only 2 conversion factors, because there are only 2 stepping stones. The first is Avogadro's number. And I know that Avogadro's number is 6.02 times 10 to the 23rd, whatever, equals 1 mole. In this case, 6.02 times 10 to the 23rd molecules. So I'm going to put molecules down here. And mole up here. And I'm not even going to put the numbers yet. Okay, that'll get me from C to D. I have moles of water here. The next one is the molar mass of water. I know that for the molar mass of water, it's 18.0 grams. 18.0 grams equals 1 mole. So mole is going to be on the bottom. See how I have moles here? Moles got to be on the bottom here. And then grams is going to be on top. Dimensional analysis. Now all I got to do is put in the numbers. I'm going to put 1 here, and I'm going to put 6.02. 23rd. Now, let me show you how you do this in your calculator. E to the 23rd, E to the 23rd, okay? And then 18 grams is 1 mole. I apologize that my writing isn't very good, but let me show you how you would do this in your calculator. Let me bring a calculator up real quick so that you know how to punch this in, because when you're doing exponential notation, it's not always easy to do this correctly in your calculator. So let me bring out my calculator real quick. I should see that. So I'm going to put 4.02. This is my scientific calculator mode. Okay. I'm going to put 4.0 because that's the question times 10 to the 21st. Don't use this. Don't use this key because that's a function. It does the log base 10. Use this key right here, EE. That'll give you the exponent. And then I'm going to put 21 because that's my number. That right there is 4.0 times 10 to the 21st. You want to use, you should find in your calculator a double E or an EX key. Don't use this number. Don't use this function. Use this because this is part of making the number an exponent. Then I'm going to divide by 6.02 exponent 23. That's Avogadro's number. Okay, and then I'm going to multiply by 18. Then I'm going to hit equals. That's the mass, 0.119. I think I need to round this off to significant figures. 0.12 grams of water would be my answer. Again, I want you guys to know that when you're writing exponent 4.0, use this key right here to make it an exponent. Because if you don't do that and you do 4 and then do this, see how that is actually a function? It's like taking a square root of something. You don't want to use that function. You want to use, that's what this function is for in your calculator. It takes a number and makes it an exponent. So that would be, let's clear this, 6.02 exponent 23. If I need to put a negative in front of that, then there's I think there's a sign change here, there. Okay, that's important because if you don't do that and you use this instead, most likely you're going to be off by a factor of 10. So it's 8:30 right now. If you guys have any, oh, I might as well do this since you guys made the effort to attend. Let me just summarize each of the chapter, and then if there's no other question, we'll be done. Chapter 1, the most important part of that particular chapter is scientific method. Make sure you understand what are the components of the scientific method, okay? That you have to have an observation or a question, that you're going to have a hypothesis. A hypothesis explains, it's not just a statement. It has to explain the observation, or it has to answer the question with an explanation. If it doesn't say a because, then it's not really a hypothesis. A hypothesis tries to explain what you're observing or tries to explain the question. Then you do the experiment to validate the hypothesis, okay? And then you go back and you make other questions, and then that cycle keeps repeating, okay? You have the observation or the question, the hypothesis, the experiment. You could also throw in a prediction. If you do that enough times, then your hypothesis is more concrete and it becomes a theory, okay? Whenever you have a statement that always states the fact, nothing else is going to break it down, then that's a natural law. For example, matter cannot be created or destroyed, it's only converted from one form to another. It doesn't explain, it just tells you what's going on. Energy is conserved, that you can't destroy or create energy, you can only convert it from one form to the other. That's a statement. It doesn't explain why you can't do that, why you can't create energy, it just tells you what it is. Those are natural laws, Okay, so the first part is probably the most important part of chapter 1 is understanding the scientific method. Chapter 2 is really the heart of doing calculations. You got to make sure you understand precision. You got to make sure that you understand significant figures. You got to know the rules when you apply significant figures. If you're adding and subtracting, you round off your final answer based on the less precise value, the one with the fewest digits past the decimal, because that has the biggest error. On the other hand, multiplication and division, you round off your answer based on the fewest significant figures. Those are different rules. Those are different rules. You should also know the metric system. Okay, you should know what the prefix means. Kilo means 1,000. Micro means 1/1,000,000th. Okay, milli and kilo are opposite extremes. Whereas kilo is 1,000 grams, a milli is 1/1000th of a gram. It takes 1,000 milligrams to equal 1 gram. Okay, it takes 1,000 grams to equal 1 kilogram. So make sure you understand those prefix. Make sure, especially, that you know dimensional analysis. If you don't know dimensional analysis, I don't know what to tell you, because that's the fun. If you're going to go into science, if there's anything you get out of this course, dimensional analysis is one of the things that you really need to understand. It'll help you in so many of your courses, okay? Chapter 3, there's 2 legs of chapter 3. One is matter. Know the classification of matter, that we have homogeneous and heterogeneous mixture, know what compounds are, know what elements are, know what physical change and chemical change are, okay? We're just talking about matter here. Know about phase changes of matter. Know about when you heat matter, then it can go from a solid to a liquid to a gas, how much energy it requires to convert water from a solid to a liquid to a gas. Those are called specific heat and heat capacity. That's the heating cooling curve, okay? We had a problem just now about calculating the energy from food. That's an important part of chapter 3, okay? So heating cooling curve is an important part of chapter 3. Calculating caloric values is an important part of chapter 3. Classification of matter is an important part of chapter 3. Chapter 4 is all about the atom and knowing about the nomenclature of the atom. Know how to read the periodic table. Know, based on the heading on the periodic table, how many valence electrons there are for that series of elements down that family. Know where your non-metals are, know where your metals are, know where your metalloids are, okay? If you are given an atomic number and a charge, you should be able to figure out how many electrons there are. That's chemical nomenclature. So understanding how to read the periodic table, know that the elements on the bottom of the periodic tables are much bigger than the elements on the top. Why? Because they have layers of shells, and the shells represents the place where electrons are found. So the more shells you have, the bigger the atom. As you go across the periodic table, however, you're keeping to the same shell. You're just adding more electrons. Actually, as you go across the periodic table, the size of the atom shrinks. Why does it shrink, even though you have more electrons? Because you're also increasing the number of protons. And the protons are, with more protons in the nucleus, it's attracting those electrons with a greater efficiency, which draws that electron cloud closer in. Okay, so chapter 4 is about the atom, the electron configuration of the atom. Know about Hund's rule, Pauli exclusion principle, paramagnetism, diamagnetism. That's part of the atom and how we do that. Chapter 5 is nuclear chemistry. Know how to balance nuclear equations. If you look at my equation page, know the nomenclature for the different subatomic particles so that you can balance them. Know disintegration series. Know about how much do you have after a certain half-life of a chemical. Those are calculations that you can easily do based on the fact that half-life tells you that for a certain amount of period, the half-life, the mass decreased to half its original value. Okay. Chapter 6 is a big chapter. Not only do you need to know how compounds come together, so you can write the formula. Remember, when compounds come together, it's got to be electrically neutral. The positive has got to be equal to negative. You also got to know which chemical the common charge are. Like, for example, magnesium is always positive too. Why? Because it's got 2 valence electrons. It wants to get rid of those 2 valence electrons. Now it has 2 more protons than electrons. It's positive too. Certain elements that will always have fixed charge. And you saw that in my supplement information. Those were the elements marked in yellow. Other elements like the transition metals, sometimes they don't know what to do. They give up 2, they give up 5. It depends on what they're combining with. You have to figure that out. In nomenclature, we indicate that by the Roman numeral in the name. So chapter 6, you have to know how to write the formula. You got to be able to know how to name the formula. Okay. That's only the first part. You should know the charge for the ones that are fixed. Certain elements will always have a fixed charge. Group 1 will always be positive 1. Group 2 will always be positive 2. Zinc, silver, and cadmium will always have fixed charge. That was in a chart that I gave you. These were the ones in yellow. Okay. Look in the equation page that I showed you, because these things will have fixed charge. The others have variable charge. The nonmetals will always be negative. Fluorine, chlorine, bromine, -1, oxygen, sulfur, selenium, -2, nitrogen, phosphorus, -3. Why are they minus versus positive? Because they want to gain electrons to have the same number of electrons as a noble gas. The name of the game when compounds are formed is elements want to give up electrons, gain electrons, or share electrons so that they have the same number of electrons as a noble gas. That's the key for them being stable. And when they can do that, they form compounds. So once you know how to write the formula, then you can do the Lewis structure. In the Lewis structure, make sure you know how to do the bond table, because the bond table actually gives you all the answers that you need. It tells you how many bonds a compound will have. It tells you the total valence electrons that you have for that compound. It tells you how many lone pairs you're going to have. And then it's just a matter of putting it together so that each atom has an octet, except for hydrogen, which is happy with a duet, 2 electrons. Once you have the Lewis structure, then you can go to that chart that I provided in chapter 6 and figure out the geometry. Depending on how many spokes are coming out from the central atom, you can figure out whether it's linear electronic geometry, trigonal electronic geometry, or tetrahedral electronic geometry. And then depending on how many of those connections, we call them electron domains, have bonded atom and lone pairs, you can figure out the molecular geometry. So if you use that chart, it makes life easier. Then you can tell me the bond angle based on whether your molecular geometry is linear, it would be 180. Trigonal, planar, it'd be 120. Bent trigonal, it'd be 120. Pyramidal, that'd be about 109.5 approximately. Tetrahedral, 109.5. Bent tetrahedral, 109.5. If the skeleton is tetrahedral, the bond angles are approximately 109.5. If the skeleton electronic geometry is trigonal planar, the bond angle is approximately 120. If the skeleton is linear, then the bond angle will be 180, okay? From the molecular geometry, you can see whether or not that chemical is symmetric or non-symmetric. Why is that important? Because if it's not symmetric, then that means that the electrons are going to bunch up to one side, and that makes the chemical polar. But if it's symmetric, all the atoms at the end are identical, the central atoms are identical, it's totally symmetric, then it's a non-polar chemical, okay? It doesn't act like a magnet. When you have a magnet, you have North Pole and South Pole. It's called polar. when you have a molecule that's polar, it means one side of the chemical has more electron density than the other. It acts like a magnet because one side's partially negative, the other side's partially positive. Whenever you have a situation like that, then that chemical has dipole-dipole intermolecular force. Whenever something is polar, it's got dipole-dipole intermolecular force. All molecules will have London dispersion force because all chemicals will have electrons. And then special chemicals that have hydrogen bonded to an electronegative element like fluorine, oxygen, nitrogen, or chlorine. It's got to have hydrogen though, bonded to these electronegative elements. Then you can have hydrogen bonding. Whenever you check off hydrogen bonding, you better check off dipole-dipole and London dispersion force. Okay, because chemicals that have hydrogen bonding are also polar. And then they have electrons, so they have London dispersion force. If the chemical don't have hydrogen bonding, but it's polar, then it's got polar and dipole, then it also have London dispersion force. All chemicals have London dispersion force. So you should always check mark that off. Okay, that basically is chapter 6. It's the essence of understanding molecular compounds and molecules and all that. And then in chapter 5, what we're doing is putting it in a reaction, know how to balance the reaction, know how to identify the reaction, and then know how to do stoichiometry. Okay.